Hi everyone, I'm Renjie Zhang. Today, I'm very excited to present you with my thesis topic, dose prediction for radiotherapy using deep learning models. First, let's begin with understanding what is radiotherapy. It is a treatment method to use high-dose radiation to kill cancer cells and reduce tumors. As a branch of artificial intelligence, deep learning has demonstrated its power in medical image recognition tasks. It can help doctors to deliver a more efficient and precise cancer treatment plan and provide robust support in clinical decision-making for diagnosis and treatment. In Australia, radiotherapy is used in more than half of cancer treatment. 50% of patients receive treatment within 10 days, and 90% within 27 days of being assessed as ready for care. However, for cancer patients, every minute and every second are important. Globally, we hope to shorten this time even more through deep learning. This is why AAPM hold an international competition that drives those dose prediction in radiotherapy at 2020. It's not just a contest, it's a platform that provided an open source dataset and a standard matrix for relevant research. The challenger gathered the DICOM files of 217 patients from the Prince Margaret Cancer Center, which located at Toronto, Canada, ensuring that the researchers are aligned with the real-world data and clinical scenario. Based on the dataset, the competition organizer Aaron Bober has proposed a GANs model. It divides the 3D CT images into 2D slides and uses the Unite generator to generate the dose distribution and make a prediction based on inputted slides. Other researchers have also proposed some innovations based on Unite architecture. Unite is a popular architecture in medical images as it is able to identify specific structure and regions within an image, such as tumors, organs, or blood vessels by its contracting and expansive pathway on limited dataset. The Unite model, especially the HD models, takes this further. Dense convolution, stratified convolution for downsampling, and upsampling with concatenation. All these techniques contribute to a model that is both robust and accuracy. However, we recognize that the most models in relevant research did not incorporate the attention mechanism. To address this research gap, we combined the following two baseline models with attention mechanism. The first model is cascaded 3D model. It is a dual Unite architecture with multi-scaled feature extraction. The second baseline model is DCNN. It uses a dense feature aggregation block to emphasize its ability to capture context and long-range relationship in tasks. Innovation is the heart of our methodology. Try to improve the performance of both baseline models. I select two attention mechanisms and integrated with them. The first one is the spatial attention mechanism. It is a traditional attention module. The second one is the SIMA attention module, a simple parameter-free module that uses the neuroscience-based theory to find the importance of each neuron and avoid too many efforts for structure training. The training of our model involves a dataset of 200 patients provided by OpenKPB grant challenger, including CT data, dose distribution, structure mask, and voxel dimension. The validation dataset with 40 patients allows for fine-tuning, while the testing dataset featuring 100 patients provided by the robust stage for performance evaluation. Our training environment, including tools like PyTorch 1.2 and Python 3.8, also hardware like GPU A100, which was rented on the clouded service AutoDL. The evaluation matrix including the dose score, which measures the mean absolute difference between the predicted dose and the ground truth dose. DVH score, it evaluates the dose distribution within specific region of interest. A smaller score generally means better performance here. It should be noted. After training, I have made the dose prediction and I'll compare it with the ground truth dose to help you better understand the prediction result. Here is some visualized outcome. The left is a CT image. The second column is predicted dose by our model. The third column is the ground truth dose. The last column is the different map. Here is the DCNN attention model for patient 288. And this is the prediction report about the DCNN SEMA model for patient 296. Again, this is the prediction visualized result about the cascaded 3D attention model for patient 298. And lastly, it's a cascaded 3D SEMA model for patient 251. After all, we can see that our prediction is very close to the ground truth dose in clinic use. Now, let's move on to the quantity result analysis. For those two tables, we can see that attention mechanism improve both baseline models, particularly SEMA. 3D model outperforms 2D models, but takes longer to train and requires more computing resource. Cascaded 3D SEMA shows the best dose score at 2.43. DCCN SEMA improves the DVH score the most by 3.5%. And compare with the Grand Challenger final leaderboard, our cascaded 3D SEMA model achieved a top 2 ranking, while the DCNN SEMA stood proudly in the top 5. Through the research, it was found that attention mechanism significantly improved the performance of both baseline models. It also exists in the result of the most participants in the competition. Among them, the performance of the SEMA attention mechanism surpassed traditional models, and it has a shorter training time compared with the traditional model, which will greatly inspire the clinical application of deep learning. But it should be noted that the model's performance is currently limited to head and neck cancer dataset, which uncertain result in other cancer treatment area. In the future, we could test it on the other dataset, like lung or brain cancer dataset. Models are also trained with the fixed beam configuration in the computation. Real-world clinical practice involve a wide variety of beam configuration, which might not align with this model. At the same time, the model's training only considered the imagery and related dose data, but there are many factors that affect cancer, such as the patient's age, gender, medical history, medication, etc. Those factors can also be collected and added to the model future training. Although the role of AI plays in human history is increasingly controversial recently, but I believe that AI will continue to drive the development of medicine and save the lives of more and more patients. In the end, I hope we can build up a better world together with AI. Thank you so much.